So on number 12, we're going to simplify this third root function. Now there's different ways of doing it. Let's zoom in on it. So one way of doing it is to think the third root of 135. Could we do that? Is there a number times itself 3 times that gives you 135? And the answer is no, right? 5 times 5 times 5, that's 125, not 135. So if you could find a perfect cube number that will work to give you 135 with multiplication, you might as well do that. So let me explain what I'm talking about here. Like for example, I know that 8 is a perfect cube number. 2 times 2 times 2 is 8. Okay, so is 135 divisible by 8 on a calculator? No, it doesn't work. So that perfect cube number didn't work. Maybe 3 times 3 times 3. What's 3 times 3 times 3? That's 27. So 27 is the next perfect cube number. Let's see if that works. If I take on a calculator 135 divided by 27, hit equal, guess what? It's 5. So what does that mean? That means that this third root of 135 could be rewritten as 27 times 5. Now, why would I do that? Well, because 27 is a perfect cube number. Okay, and you know what? The x to the fifth, I'm just going to write it over here on the side. It's the third root of x to the fifth. I'll deal with that later. Let's first deal with the number that's out in front. So again, 135, we rewrote that as 27 times 5, and we figured that out with the calculator. And now we're going to split the third root. So we're going to have the third root of 27, and we also have the third root of 5. Okay, and the third root of 27 is the nice, beautiful number 3, no more root. And the third root of 5, we're going to have to leave it, the third root of 5. Okay, now what about this other guy over here, the third root of x to the fifth? Well, I hope you guys remember that any base, so this is like a side note right here, any base that has a rational exponent, a power over root as an exponent, could be converted to a radical, or a radical could be converted to a rational exponent. What I'm trying to say is x to the fifth, that's the base, and we obviously have the third root, so there's going to be a 3 on the bottom. You could put the 5 on top, or you could keep the x to the fifth on the inside of the parentheses. So let me just do one step at a time here. Let me rewrite x to the fifth in parentheses, and then to the power of 1/3, because the third root is the power of 1/3. Now at this point you could multiply the power with the power, and you will get, let me zoom in on that for a while, you will get x to the 5/3, because 5 over 1 times 1 over 3 is 5 over 3. And 5/3 is a mixed, it's an improper fraction. So let me rewrite that as x to the 1 2/3. Where did I get that from? Well, this is saying 5 divided by 3. 5 divided by 3, it goes in one time. You're going to have a remainder of 2, so that's why there's a 2 over 3. So it's really 1 2/3. So that's how I got the x to the 1 2/3 power. Now, what does that mean? That means that x to the 1, that's simply x, and x to the 2/3 power is still there. Okay, but the x is now by itself, no more root on it. Okay, so what we really have is the third root of x squared. Again, the third root of x squared, or x squared but with the third root on it. So let's put these guys together. So far I have this 3, that's a nice 3. I have this x, that's a nice x, so I have 3x. And then this guy, I'm going to write it right here, the third root of 5, and this guy is really the third root of x squared. So let me put that x squared on the inside, and it's already in the third root. So this would be my final answer. Guys, if you're still confused about this, ask me questions. That's why we still have class. Ask me, stop in during advisory before school, or during class, okay? I hope this helps. Let's jump to part B over here. Okay, so once again, it's a good idea to know this fact, that any base to a rational exponent will have a power over root. If you have an exponent that's a fraction, the numerator is the power and the denominator is the root. So with that said, this is really going to be the denominator 3, and the power 4 is going to be up here, but that's only with the x term, okay? First, let's try to break this down with the calculator. If we think about perfect cube numbers, like 8, because 2 times 2 times 2 is 8, maybe 750 is divisible by 8. Let's see. With the calculator, it doesn't work. Maybe the next perfect cube number, 3 times 3 times 3, that's 27. 27, let's see if 750 on a calculator is divisible by 27. And it's not. Let's try the next one, 4 times 4 times 4. That's 64. So let's try 750 divided by 54. Doesn't work either. But if we think about 750 divided by 125, because 5 times 5 times 5 is 125, so 125 is a perfect cube number. So technically, I'm going to rewrite this 750, well, let me write this x to the 4th over here on the side. I'll deal with that later. But the 750, I'm going to rewrite it as 125, that's a perfect cube number, 5 times 5 times 5, times, what is it, 6. So let's put the 6 right there, and now we could split the third root of 125 times the third root of 6, which we can't do. This really is 5, so we have 5 third root of 6, okay? And over here, this third root of x to the 4th, you know you could rewrite it as a rational exponent. So you're gonna have the same base, the powers 4 over the root 3. And again, on that, you need to think of that as an improper fraction that you want to turn it into a mixed number. So you're going to divide 4 divided by 3. If you do 4 divided by 3 on the side, it'll go in one time. That's 3. You'll have a remainder of 1, and you put the remainder over the original divisor. So this is really x to the 1 and 1/3 power, okay? Now, when you say x to the 1 and 1/3 power, that's really an x times x to the 1/3. And what we've accomplished by doing this is that you have now an x that doesn't have a cube root on it. This x still has a cube root on it, but this one over here is now outside the cube root, okay? So let's go back to what we had. So let's keep this in mind. We now have an x here and a cube root of x. And we need to multiply it with this guy over here. These two I need to multiply together. So this 5 right here times this x over here is going to be 5x. So we have 5x. And then let's multiply the cube root of 6 times the cube root of x. In other words, just put them together underneath one cube root. That'll be the cube root of 6x. Ladies and gentlemen, that's the answer for that one. I hope this helps. Again, please ask me questions if you're still confused about this. Let's continue on to number 13. Okay, we have a bunch of radicals here. The way to do this would be to simply simplify anything possible. See, a radical is kind of like a variable, right? It's like if you had an x, this is totally different than this one. So you can't add x plus y plus z. They have to be like terms. Like if this is a square root of 3 and if this were square root of 3, then you could add them together because you have like terms, but they're not both square roots of 3. So what you have to do first is look at each radical and see if you could simplify it. Like you can't simplify this one, but this one you could. This one's not a perfect square number, but if you rewrite it with multiplication, you could pull out, or you could rewrite it as 4 times 3, and when you split the root, you end up with the square root of 4 times the square root of 3. The square root of 4 is a nice, beautiful number 2. The square root of 3 stays the square root of 3. And the first one, we just bring that down, and that'll be square root of 3. And don't forget about the plus sign that's in between them. And let's simplify the next one. The square root of 18, that's not a perfect square number. If it were the square root of 16, we'd have a nice answer 4. But the square root of 18 doesn't work. It's not a perfect square number. But when we think, let's break it down with multiplication so we could get a perfect square number. So what would it be? Let's say 4 times something? No, 9. Yes, 9 times 2 gives you 18. And if you split the root, you will end up with a 3 all by itself, no more root, with the square root of 2 right behind it. Okay, and let's not forget about this negative sign, so let's bring that down. There's your negative sign right there. And last but not least, the 98. Okay, 98. If it were, let's say 81, then you could square root 81, you'd get 9, but 98, you can't do it. So you want to rewrite it with multiplication so you could get a perfect square number. So you might want to try, you could use a calculator. Let's go with 98 divided by 4, because 4 is a perfect square number. It does not work. How about 98 divided by the next perfect square number, 9? That's not going to work. 98 divided by 16. Let's see, 98 divided by 16, and that doesn't work either. 98 divided by 49, that works. 49 times 2 is 98. So let's rewrite this as 49, that's a perfect square number, times 2, and let's split the square root. So we're going to end up with a 7. The square root of 49 is 7, no more square root, with the square root of 2. So you have 7 square root of 2. Let's not forget about this plus sign. Let me bring that down. There's your plus sign between them. So now that they're all simplified, now you could combine the terms that are alike. There's a square root of 3, there's 2 square roots of 3. So when you think about it, it's like saying x plus 2x's. Well, that'll be a total of 3 of those square roots of 3, okay? And we can't combine it with these other ones because these are square roots of 2. But over here, we could combine this negative 3 square root of 2. Maybe I should use a different color. Negative 3 square root of 2 plus 7 square root of 2. That's like saying a negative 3x plus 7x. That will be a positive 4x. But in this case, positive 4, it's not x's, it's a square root of 2's. So this is your final answer for this one. For the sake of time, I'm not going to do B or C right here. You guys could try it. If you guys have questions, come and ask me. I'm moving on to number 14. So right here, we do have A up on top and A on the bottom. We just have different exponents. So let's understand something before we even try to do this one. If I have A up on top and an A on the bottom, what happens? They cancel out, right? That would become 1. But what if you had an A to the 5th over an A to the 3rd? That really becomes a subtraction problem. And we also remember that when you take a value and move it up, the exponents change signs. So A to the 5th divided by A to the 3rd is really A to the 5th times A to the negative 3. Isn't that right? I hope we see that when we take this A to the 3 and move it up, it becomes A to the negative 3. So you really have A to the 5th times A to the negative 3. And now you could use rule 1 of exponents, just focusing in on this. What's A to the 5th times A to the negative 3? You simply add the exponents and you'll get A squared, okay? So all of that is just practice for what we're about to do on options, or on practice A right here. So I'm going to take the A to the 1/2 and I'm going to move it up, and of course the exponent becomes negative. So I'm really going to have A to the 3/4 power times A to the negative 1/2 power. And now that I have the same base, A right here and A right there, I'm going to be able to combine the exponents, right? I'm going to be able to subtract the exponents. 3/4 take away 1/2, and that's pretty challenging on its own. So let me write down 3/4 take away 1/2. Of course, you're going to need a common denominator, so you're going to have to change that by multiplying by 2, multiplying by 2. You're going to get 2/4. So instead of 1/2, you have 2/4. So now you have the same denominator, and now you could do 3 subtracting 2. That's going to give you an answer of 1/4. So ladies and gentlemen, we are talking about the exponents, right? So the final answer is A to the 1/4 power. Now that's the answer, A to the 1/4 power, but maybe on your multiple choice options, they write it as the 4th root of A, because either one of these is the same thing. You just got to look out for both of them on multiple choice. So I hope this helps. We'll continue with this on the next video on number 15, which is solving quadratic, not quadratic, square root inequalities.